Now, the creativity aspect, phenomena in the borderlands between the theories. There's an abundance of them in quantum physics, and I'll just tell you one. A quantum borderland phenomenon, the statistics of high excited energy levels. Well, one such statistic is the distribution of spacings between adjacent energy levels. So here's a spectrum of a molecule, for example. Here are the high excited states. Much molecular physics is concerned with ground states, or the first few, but there's also interest in the high excited states. And these are intrinsically borderland because, first of all, they're quantum because you're talking about separate energy levels. But high levels, you're near the classical limit. So we're in the regime that I'm drawing attention to. Here's a spacing S. You know the average spacing. Let's look at it through a microscope. So the average spacing is 1. But individually, these spacings fluctuate. And the probability of spacing, P, probability of spacing, is what we're interested in. Now, there's a beautiful phenomenon. This spacings distribution, and I can see I can't spell, exhibits universality. That means it doesn't matter what the system is, except for the type of chaology that it exhibits. Now, the first universality class, systems that are classically not chaotic and have more than one degree of freedom. Well, for example, take a circular drum, a circular boundary, and it could be a quantum dot, for example. Look at the excited states. It's the same problem mathematically as the frequencies of vibration of a circular drum. Well, here's the spacings distribution. This is the spacings distribution, curiously enough, but for a reason, that of these non-chaotic motions, is that this is the spacings distribution of random events. It's like waiting for a bus in Bristol. The most probable interval between two of them is actually 0. Right. Now, the second class is all systems that are classically chaotic and time reversible. This was shown by Chris, vibrations of a stadium. Pull them apart, proven to be chaotic, completely different. There's the distribution. The energies actually repel each other. There's a diminishing probability of getting smaller and smaller spacings. The third class is if you have systems that are classically chaotic and not time reversible. I should have said there's a mathematical theory called random matrix theory which describes this type of statistic. The third class, classically chaotic and not time reversible. Take a stadium, charged particle, put a magnetic field in it. You get repulsion, but it's stronger. It's quadratic at the origin. These three, there's another one, it doesn't matter what it is. That also comes from random matrix theory. So these are borderland phenomena in quantum physics. Is one example of a class. There are many, many of them. Don't have time to describe more. Now, the third part, number. It seems completely different, but I'll explain the connection. Connections are very important in science. They're not optional extras. We're always delighted when we find apparently completely discordant areas have similar structures, and we've seen a number of examples already today. I want to quote Charles Frank, my late colleague. Physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. And here's a provocative example, apparently completely unrelated. Prime numbers, here they are. I once, many years ago, gave a talk including this aspect, and afterwards a young man came up to me and said, "Professor, if you give this talk to mathematicians, I suggest you don't include 21 on your list." I have learned. Well, they're the atoms of arithmetic, so one should know everything about them. Well, depict them as a staircase. That's the number of primes less than x. Jumps by 1 every time you encounter a prime. And there are infinitely many of them. Euclid knew that. They thin out very slowly as you go higher, but they also fluctuate. Now, if you look at 10,000, you can't see the fluctuation. You see this beautiful, gently, slightly sloping less than 1 curve. Well understood by mathematicians. But if you zoom in, you see these fluctuations, and one would like to understand them. They look random. They do have a structure, and that structure is related to a set of different mathematical numbers, which I won't explain exactly where they come from. They're called the Riemann zeros. And here are these, the first few of them, numerically as numbers. And again, there are infinitely many of them. The density of them increases slightly, slowly, as you go higher and higher. Now, there's an important unsolved mathematical problem called the Riemann hypothesis, one of the most important and frustrating, tantalizing mathematical problems today, which is that these are all real numbers. If you want a physical or a common language understanding of the Riemann hypothesis, think of these numbers. Oh, excuse me, sorry. We know the first 10 trillion are real. We know infinitely many of them are real. We know that at least 40% of them are real. But that's not a proof. There could be some ones that are not real. They would come in pairs very high up, but nobody knows. To make common language understanding of this, think of these numbers as frequencies. If they're real, they're definite frequencies. If they're complex, they're slightly blurred out. Think of any sequence with well-defined frequencies, call it music. So the Riemann hypothesis says the primes contain music, 4 words. That's, by the way, it's horrible. If you play it, it sounds awful. I'm not going to play it now. But there are related sounds. I call this ear math. They're listening to mathematics rather than seeing it. If they're related sounds, then you do get interesting sounds, but not the primes themselves. Now, frequencies. Why have I said that? So there are strong hints from a mathematical analogy that the Riemann zeros are vibration frequencies or energy levels of some unknown quantum system in the third universality class. I want to show you the evidence for that. The spacings of these numbers near the 10 to the 20th beautifully fits random matrix theory, quantum chaos theory. Beautiful. But it goes wrong. If you go beyond the first few neighbors, random matrix theory fails, and here is a statistic that measures that very precisely. It's called the number variance. Imagine that you're looking up near these very high Riemann zeros, and you take a stretch where on the average, and you know the average behavior, you should get a number L of them length. Of course, you won't every time, the number will fluctuate, and the mean square deviation as a function of this separation is this quantity. Well, look, here it is. Random matrix theory predicts it grows in this way, but the Riemann zeros, after the first few, well, we've already seen that mathematics agrees, begin to deviate. Now, it turns out, it's a beautiful fact, that in quantum chaology, I didn't describe this, but this universality also fails for longer range statistics in ways that are well understood, related to the periodic orbits of the chaotic system. Chaotic systems, most orbits are not periodic, but some are, and we know about them. They're unstable, there are infinitely many of them, and it's their structure that causes the deviations. They're not universal, at least the short ones are not. Right. But the analogy with the Riemann zeros fails in exactly the same way, with the periodic orbits of this unknown system replaced by individual primes. In fact, the periods of these periodic orbits that we dream of are multiples of logarithms of prime numbers. Well, we have a quantum theory of the deviation. Let's apply it to the Riemann zeros and look at that function beyond the first few where you see that deviation. Look at the number variance. Look, random matrix theory. it's useless beyond a few, going up to 100. But here, and there are two curves that you can't see because they're so close together. One is the Riemann zeros, and the other is the quantum-inspired analog theory. Very good. Well, let's continue this. Let's look at 100 near 500,000 spacing. Well, there we are, still continues. By the way, these peaks here and previously, these peaks, we're talking about distributions of Riemann zeros near the 10 to the 20th. These peaks are actually related to the lowest Riemann zeros. It's a wonderful duality. It's a mathematical phenomenon called resurgence, which appears in many different areas, but this is an example of it. So this works, you know, it's evidence of the fertility of the analogy between arithmetic and quantum chaology. But the basis of the analogy is this known unknown. That's the underlying quantum system and the chaotic classical dynamics underlying it. We know a lot about it. You know, I told you, periodic orbits we know it's chaotic. It doesn't have time reversal symmetry, so it's analogous to a particle in a magnetic field. We know that its chaos is uniform in the sense that wherever you look in the relevant space, the exponential divergence of trajectories of the system, we don't know what it is, will be uniform, will be the same. We know lots of properties, enough to apply this quantum analogy, but we don't know what the system is. And there are one or two mysterious loose ends which don't quite fit. Okay, so the Riemann hypothesis could be false. You know, a leading mathematician, he came to Bristol, and as I drove him from the station, he said, "Why do you physicists all believe in the Riemann hypothesis?" And I said, "I don't believe in it. I don't know. It'll be more interesting, actually, if it were false, because there will be a reason why, if I can express it in a religious way, why God is so malicious as to tempt us into believing that this Riemann hypothesis is true, everything fits, but then at the last minute it will be wrong. Maybe that's the reason why it's so difficult, because it's not true. So it ain't over till it's over." I finish with Pete Hine. "Problems worthy of attack prove their worth by hitting back." Thank you.